Very good evening and warm greetings. We are from Group A4, Unit Operation Lab 2. My name is Kubayb Al-Awadi and my group mates is Kamish and Hisham, Human and Satish. And today we will be presenting about experiment 3, which is the residence time distribution in back bed, which we use as our process is ammonia stripping through wastewater treatment. In today's presentation, we have 9 sections. We will be presenting first on introduction, objective, customer requirements. Then we move on to process description of the plant, process flow diagram of the plant, the equipment list, unit description, which will include as well the results, safety and other consideration, end up in economy analysis, and then. So in the first section, which is the introduction, I will give some explanation about the residence time distribution of a chemical reactor, packed bed reactor, RTD application, and the stripping of ammonia in wastewater treatment. Basically, the basic definition of RTD is the probability distribution function of a time a liquid could spend inside the reactor. RTD is used to compare the behavior of real reactors to the ideal ones. When we use the back bed reactor, is to compare to improve the contact between chemical bases in a chemical process, such as stripping of ammonia in wastewater treatment. The most basic definition of stripping is a separation process where one or more components are removed from a liquid stream. The objective of our experiment is using the back bed reactor to determine the effect of liquid and gas feed rates on the mean residence time and intensity of liquid-based axial dispersion. Second object, which is the LTD application, is to reduce ammonia and reusable or returnable water through wastewater treatment. So in customer requirements, we have the importance of water. Basically, the water is one of the most important assets in our social and economic development. The importance of ammonia needs in our daily life, such as in fertilizer and improvement of the plant, refrigeration and air conditioning as well. The constant and rising issues that due to the growth of population and economic crisis, this pushes the limit of water resources and ammonia resources. So a need of sustainable process and effective technologies to produce and overcome such crisis of water, resources, and ammonia. That's all of my part. Thank you very much, and I would like to pass the floor to Mr. Kamish.
Very good evening to our lecturers. Thank you, Gopal, for explanation of the first part of the report. Now, my name is Kamish, and I'll be talking about the process description and the PFD diagram of the process that we have chosen, ammonia stripping in wastewater treatment. Before I talk about the process, let me just show you the PFD diagram itself. So, we first collect our storage, the wastewater, in a tank, which is here, and it is then sent to the next tank, the pH and the filtration tank. What happens in this tank is that the wastewater is checked for its pH and the presence of heavy metal. This is because it needs to be in optimum pH so that the stripping can go at a maximum efficiency. And if heavy metals is present, it can hinder the column here, which means that it can damage the column over time. So that is why heavy metals must be removed at this tank itself. And then it goes to the clarification tank, which also is a standby tank. What does this mean is, once you check for the requirements at the pH and filtration tank, the clarification tank will store the wastewater which has been treated, pre-treated, so that it can be ready to be sent to the absorber column, which is the stripping column, which is this. Now, what happens when it enters the stripping column is, it enters the top part with wastewater containing ammonia and the air, which is containing light results of NaOH. It enters to the bottom. It will pass through this column and it will be somewhere around the pad column, around in the middle. You can see that. And the ammonia will be channeled out, will be displaced from the wastewater and channeled out to the absorber column. The wastewater, which is now clear of ammonia, which is clear of heavy metals, will then go back go out through the bottom, and it will be reused or recycled by the industry for many purposes. The ammonia now, that is channel on the top, will enter the absorber column. Like this, inside there is a closed loop system where what happens is the ammonia forms ammonium sulfate, and it is stored in the ammonium sulfate storage tank, which then can be used as a fertilizer for the industry itself, or can be sold for profit, making this process a feasible and a profitable process. Before I end my part, let me just recap. Wastewater is collected, it is tested for pH and presence of heavy metal, sent for clarification tank for standby, goes into column for stripping process, the first column. Ammonia goes to the absorber column where it is made into ammonium sulfate. The water free of ammonia is recycled again. Ammonium sulfate from absorber, the last column there, is sent to the storage tank, making it ready to be sold by the industry as fertilizer, or it can be reused again, depending on what the industry wants to achieve in the end. Thank you very much.
Okay, a very good evening to our lecturer and to all of you. Thank you, Mr. Kamesh, for your explanation earlier. Now it's my turn. My name is Hisham, and I will be talking about the results. And I will be talking about how our experiment, RTD in tubular flow, relatable to our application process that we selected, which is the stripping ammonia. Now, this is the table for the counter current, and this is the table for the co-current for the experiment A, and this is the for experiment B, which is for the pulse input for counter current, and then for the co-current. Now, I'm talking about the graph. So, this is the comparison between the counter current and co-current in the step input. So, you can see the difference. You can see that counter current will have more conductivity than in co-current. Okay. This is because if we look at the graph, you can see that the counter current has higher graph than the co-current part. So, why this happened? Because in counter current, the flow is in opposite direction. So, which means the particle can displace more in higher efficient than in concurrent process, right? So, moving on to the pulse input. So, as we can see, it's also the same for the pulse input. We can see that the counter current will have the higher peak than the concurrent process, right? So, this is our calculation, how we find the delta N, the ET, right? So, we take at one point, we find the C. For example, we take at T equals to 1, and then we just input the conductivity, and then you find the E, right? So, and then for the residence time, we use this formula, and then for the variance, we use this formula, and then this is how we calculate the skewness using this formula S3, right? Just input and everything. So this is the technical part. Alright, and then this is how we decide whether the system is in large dispersion or small dispersion. Alright, this is how we determine the dispersion for the experiment A, the counter current, and then for the experiment A, the co-current, and then for the experiment B, the counter current part, and as well for the experiment B, the co-current part. Right. So moving on to how we comparing the stripping ammonia application with our own experiment. So moving on to this part. Okay, this is the data table for the ammonia stripping process. So this is the graph. You can see that this is the pulse. This is the stack of pulse. Alright, this is the graph for the ammonia process. As you can see here, the graph is in negative inclination, which means that this is because the concentration of ammonia is decreasing with time. Opposite to our experiment, which we use salts, and the salts and the water is moving out from the system throughout the time. But in this process, throughout the time, the salt concentration is reaching with the ammonia and making the ammonia concentration in water decreasing with time. Alright, so that's all from me. Thank you.
Good evening, my name is Satish, and as my partner Hisham explained about the result, I will now explain to you guys the equipment list and the unit description that will be explained. Now, what equipment are used? Previously, Kamesh has explained the process flow diagram. I will explain each and every equipment that is used, what it does. Now, firstly, accumulation tank. This tank acts as a storage tank where wastewater storage rich in ammonia are kept before it is sent to the filtration tank. Filtration tank has two important roles, which is to keep the pH value entering the wastewater at optimum pH of 10.8 to 11.5. Second important part is to filter any heavy metal that may be present in the wastewater. However, if pH value is higher than the optimum value, lime water will be added to increase the acidity, thus obtaining the matching the required pH value of 10.8 to 11.5. Next, move on to clarification tank. What does the clarification tank function as? It keeps the parameter in check. What are the parameters? pH value, temperature, and presence of any heavy metal. If these parameters either one are not fulfilled, it will be sent back to filtration tank to fulfill it. Then we move on to the next one, which is the stripping column. Stripping column is the most important column and where the major process of ammonia stripping occurs. The wastewater containing ammonia enters to the top of the column, whereas the air containing light traces of sodium hydroxide affect to the bottom of the column. The flow of both liquids are in a counter current step change input, where the entire packed bed column is filled with plastic made ration rings. This rings has one function, which is to increase the surface area between air molecule and the wastewater that enters. Hence, the product of this column is air with ammonia and water. The air with ammonia leaves the column from the top and the water leaves through the bottom of the column. The air with ammonia content leaves the top of the part of the stripper and enters the absorber column, whereas the water that leaves through the bottom column is recycled for other usages. Moving on, absorber column. In the absorber column, the air from the stripping column with ammonia is to form the concentrated ammonium sulfate. The clean air, once the ammonia is been removed from the air with ammonia from the stripping column, has been absorbed and recycled back to the stripper. There are two advantages of using absorber column: no air emission, conservation of energy, and one disadvantage is high initial cost and operating cost. Now, I will explain to you guys why our experiment that we did in the lab is equal to the RP application of stripping ammonia. In our lab, we did liquid filling water with traces of containing NaCl in gas feeding air. In the previous RP example, gas with air with sodium hydroxide, whereas ammonia with air, ammonia with wastewater rich in ammonia. We have done 4 experiment parts. Step change with counter current co-current, pulse input with counter current co-current. Thus, we choose pulse input, step change input of counter current for experiment to compare with the RP application. Next, we have the safety and other consideration. There are 3 safety: environment, occupational health and safety, and community safety. Environmental safety is the process of condensation of waste gases containing ammonia and other byproducts may be harmful to environment. Occupational safety is the chemical, how is it kept, and the ammonia storage failed to be kept properly will result in explosion. Finally, is community health safety, where the plant where you want to build any ammonia stripping column and thing must be well kept in an inhabited area with a residential population. If not, the gases that are released are harmful to the residential area. With that, I conclude my presentation on this. Thank you. I'll move on to Kumaran next.
Today we are going to talk about the economic analysis of ammonia stripping in industrialization. First of all, to cost out an ammonia stripping, the main criteria is the design of the ammonia stripping. which will determine the cost of the project. First of all, there are 3 to 4 important details in costing ammonia stripping, which is the hydraulic wastewater loading, pH of wastewater, water temperature, and ammonia concentration in wastewater, as I have bolded in all these criteria points. Let's talk about the design criteria, where the hydraulic wastewater loading should be at optimum at 0.1 to 0.2 liter per minute per meter cube. And extreme goes to stripping air flow rate, which is 32 to 54 liter per minute per meter cube. The packing depth should be at 6.1 to 7.6 meters. And the most important thing is the pH of the wastewater. It should be 10.8 to 11.5. The reason of the pH of the wastewater should be optimum because this is going to affect the cost of the air stripping column. The second is the air pressure drop. It should be 0.015 to 0.019 water per feet. The blower type, the site and the land requirements, packing material should be the plastics. Packing spacing should be 5 cm horizontal and vertical. And next we are going on the water temperature, as it also should be optimum. Based on certain different industry, they use different types of temperature. But for ammonia stripping, the water temperature will be affecting the cost of the air stripping column. Second, the plant capacity and the ammonia concentration in wastewater. And the last one is the waste distribution uniformity. All these design criteria affect the cost of the air stripping column. And next we will find out what is the product of stripping process, which is the ammonia. Now we are going to see about a figurative load removed according to cost. This particular table shows the unit cost for reducing ammonia for different concentration. As we can see, the more the work size, which is the population equivalent, the PE. According to the population equivalent, the wastewater will be more, so the load removed of ammonia will be a lot. These are the figurative for how much of load removed per kg, which will be in pounds. The source of this data is from Auxera, a company from UK which is very good at wastewater refurbishing, which is ammonia stripping, phosphorus, nitrogen, and many more. Next, we are going to look upon the economic analysis of the same company. This is the economic analysis summary. The capital, the working capital are quite less according to other companies because this is only been calculated for ammonia stripping, whereas they have many more nitrogen and phosphorus removal. And the operating cost is 1562K. This entire economic analysis summary defines how much does it take to produce an air stripping column. In a summary and in a conclusion, the total profit made by this particular air stripping column company will be 988,000 in Malaysian ringgits. These are the survey that we have done, and it is very feasible. Thank you. Thank you very much.
Okay, so we have concluded that we have shown that how the residence and distribution of chemical reactor, as what we showed in our experiment, can be related to our application that we chose, that is stripping of ammonia in the industry. It uses pipe-bed reactor. It has hardly application in the sense that how long the process occurs in terms of NaOH, how long it takes to displace the thing. And we have shown that based on all our presentation and the results shown earlier by Hisham, that this process is equivalent to our experiment that we did. It's a feasible process, an economical process, and it's a proven successful process. So for that, thank you everybody for watching the video.